Hello, good evening everyone. Today we will be presenting our project on time series analysis of power consumption completed for DSC425 under the guidance of Dr. John McDonnell. We are Group 3 Power, me Akanksha Singh.
I'm Yash Kumar.
Objective. So before we get into the technical parts, we wanted to give you a quick background. Our project focuses on Tetuan, a fast-growing city in northern Morocco. Because the city is expanding and country relies heavily on imported electricity, forecasting power demand, and Tetuan's weather, especially the heat, affects usage a lot. So the combination of rising demand, temperature sensitivity, and limited local production made this dataset interesting to study, and that's why we chose to work on it.
Our dataset covers the entire year of 2017 at a 10-minute frequency, so we had a little over 52,000 rows. We also have 9 variables including temperature, humidity, wind speed, and the consumption for zone 1 to 3. The nice thing about 10-minute data is that the daily pattern becomes extremely clear, but the downside is the strong autocorrelation and noise, which make many classical models behave poorly. Still, it gave us the details we needed to understand the intraday behavior, which became the core of our project.
Modeling strategy overview. First, we aggregated zones into daily totals and weather variables into daily averages, then ran ARIMA and SARIMA. Those gave us a general idea of weekly trends, but they completely missed the intraday patterns. So we switched to the raw 10 minutes data and tried VAR and ARMA GARCH. That helped us study relationship with temperature and volatility, but it didn't give a stable forecast. Finally, we tried applied regression with Fourier seasonality plus temperature as an exogenous regression, and that ended up being the most consistent approach for capturing these strong daily cycles.
When we aggregated the data into daily totals, all three zones saw strong weekly cycles. Weekdays were high, weekends lower. Sarima was the natural choice because it can model that repeating pattern directly. For zone 1, selected Sarima followed the general weekly movement well, but it struggled with sudden jumps. Zones 2 and 3 behaved similarly. The weekly shape was captured, but the models couldn't react quickly to abrupt changes from weather or local events. And this told us something important. A lot of the meaningful structure in Tetuan's electricity usage isn't happening day to day, it's happening inside the day. That's why the daily models weren't enough and why we shifted to the raw 10 minutes data.
When we looked at the raw 10 minutes series, it becomes obvious why daily models were missing so much. The intraday cycles are incredibly strong. There are sharp spikes every day, and the zones behave differently, especially zone 3. So we knew any model that didn't use the high frequency structure wouldn't be capturing the real behavior.
With the 10-minute data, we first tried a WARE for temperature and consumption. Leg selection suggested long memories, sometimes 10 to 24 legs, which fits how people use electricity. The ARMA part of the ARMA gauge models capture short-term dependence well, but the gauge layer mostly failed. The data doesn't have true volatility clustering. The spikes are operational jumps, not statistical volatility. Zone 1 and Zone 2 both saw weak temperature effects and very little volatility. Zone 3 had the biggest jumps, but even there, the gauge didn't improve much and sometimes didn't converge. So where gauge helped us understand the relationships, but it wasn't a strong forecasting tool. That pushed us toward the Fourier-based approach.
When we broke down the temperature series, the ASCF showed a very slow decay with clear waves at 144 lag mark, which matches a strong daily pattern in the weather. The PACF drops off quickly, meaning there isn't much short-term autoregressive structure beyond that daily cycle. And the EACF grid basically confirmed the same thing. There is no clean ARMA shape here. The takeaway for us was that temperature is smooth, highly seasonal driver, not a noisy one, so it's better treated as a regressor.
For Zone 1, the ACF has perfect repeating waves every 144 legs, exactly one day of 10-minute intervals. The PACF drops immediately and stays flat, meaning there's only a tiny amount of short-term memory. So Zone 1 is mostly a clean daily cycle with very little complexity that guided us toward a simpler ARIMA structure. For Zone 1, we started by checking how temperature interacts with power usage. The CCF on the left shows there is some connection, but it's quite small. You can see those repeating bumps at the daily rhythm, which means temperature isn't driving consumption. The daily routine is. People use power in Zone 1 in a very patterned way, and weather only nudges that pattern a little. On the right, the MSTL decomposition makes the structure even clearer. The raw line at the top looks messy, but once it's broken down, you see the story. The trend barely moves. The seasonal component is almost perfectly consistent every single day, and the remainder is tiny bursts of noise. That told us Zone 1 is basically a clean, predictable daily cycle with no strong long-term drift. Based on that structure, the model that ended up fitting best here was an ARIMA 312. It's a simple model, but it captures that repeating pattern while still adapting to small shifts from day to day. And you can see that in the diagnostics at the bottom, the residuals stay tightly around zero. The ACF looks almost flat, and the distribution is extremely narrow. That's what you want to see. It means the model has observed the daily pattern and the leftover noise is just random. So this slide essentially confirmed two things. For zone 1, the behavior is highly routine and a moderately flexible ARIMA model was all we needed to track those small variations around a stable daily cycle.
For Zone 1, the backtest shows that our 10 minutes model using Fourier seasonality and temperature tracks the overall intraday movement really well. The fitted line is smoother than raw data, but it keeps the correct shape the whole time, which tells us model isn't drifting or missing major shift. In the 3-day forecast on the right, you can see that the strength of this approach, the model repeats the intraday cycle almost perfectly. The peak and drops happens at right hour and the amplitude is realistic. So the main takeaway for the zone 1 is that the intraday pattern completely dominates the behavior, and once the model learned that 24-hour cycle, it produces very stable and reliable short-term forecast. For zone 2, the ACF immediately shows the same strong daily rhythm we saw earlier, the big repeating waves at 144 lag interval. That tells us zone 2 consumption is also heavily driven by the day-night cycle. The PACF is almost completely flat except the sharp drop at lag 1 and a small cluster around 144, which basically means there isn't much short-term memory beside yesterday and the daily seasonal structure. After taking logs, the pattern barely changed, which confirmed the variance is pretty stable here. Zone 2 isn't as spiky as Zone 3. The ESEF doesn't really offer clear guidance. So instead of forcing a structure from it, we use these ACF PACF behavior to narrow down reasonable IRMA components and then validated them in the next slide.
For zone 2, the CCF with temperature shows a very strong seasonal relationship. The peaks repeat almost perfectly every 144 legs, meaning temperature and demand rise and fall together over the daily cycle rather than at a single fixed leg. The MSTL decomposition makes this even clearer. Zone 2 has one of the cleanest daily seasonal patterns in the whole dataset. The trend moves slowly with small weekday and weekend waves, and the remainder is tight with only occasional bursts from short-term usage shifts. This fits the nature of Zone 2, which mixes residential and commercial activity, predictable routine, but a bit of variation in an intensity. The residual diagnostics from our Fourier plus ARIMA error model confirmed this structure. The residuals stay centered around zero. The ACF is nearly flat, and the histogram is sharply peaked, which means the model captured most of the systematic daily behavior and left behind only minor noise. For zone 2, the backtest shows that our 10-minute Fourier model follows the overall movement well, even though this zone has slightly sharper jumps than zone 1. The fitted line stays smoother than the raw data but continues to track the directions correctly, which is what we expect. Zone 2 has mixed residential and commercial load, so the intensity shifts day to day, but the underlying intraday rhythms stays stable. In the 3-day forecast, that rhythm slows up very clearly. The peaks and drops happen at the right hours, and the shape of the daily curve matches the last week almost exactly. The model doesn't chase every spike, but it captures the actual intraday cycle very reliably. So overall, Zone 2 gives us a clean, repeatable daily pattern with a bit more variability, and the model handles that balances really well.
For Zone 3, the ACF again shows the same strong daily structure with very clear 144 lakh cycle, but the amplitude is slightly weaker compared to Zone 1 and 2. The PACF drops off quickly, which tells us Zone 3 behaves more like a smooth, low memory process once we remove seasonality. The log transformation doesn't change the pattern much, meaning the underlying structure is already stable, and while the EACF grid isn't very informative. The general takeaway is that Zone 3 follows the same dominant daily rhythm, but with a bit less persistence.
For Zone 3, the CCF shows the same repeating daily pattern as the other zones, but with much stronger peaks. That means temperature affects this zone more directly, which matches what we see operationally. Zone 3 has more industrial type loads that respond sharply to heat. The MSTL decomposition confirms this. The daily seasonal component is still dominant, but the remainder is much noisier, with frequent spikes that break that smooth rhythm. The trend also shifts more, showing short, irregular operational changes. Our Fourier plus ARIMA 015 model captured the main daily cycle, but the residuals show more volatility left over compared to the other zones. So Zone 3 is still highly seasonal and temperature sensitive, just much more unpredictable, which makes it the hardest of the three to model cleanly. For Zone 3, the backtest highlights the two things that make this zone different. It follows the same intraday cycle as the others, but it also has large sudden jumps that looks more like operational switches. The model tracks the general shape but smoothes those abrupt spikes, which is expected. They are not predictable time series behavior, they are one-off shifts in demand. In the short-term forecast, the daily pattern is captured very accurately. Zone 3 rises sharply during active hours and drops hard at night, and the model repeats that timing almost perfectly. What changes is the amplitude. The peaks go much higher and the drops dip lower than in the other zones, and the forecast reflects that without overreacting. So even though zone 3 is the most volatile zone, the model still gives a reliable intraday curve for the next few days, which is exactly what's needed for short-term planning.
We faced several challenges. The structure of the data made it difficult to capture all the patterns clearly, especially because the 10 minutes frequency created very strong daily and seasonal cycles. When we tried aggregating it to daily values, a lot of important details disappeared. We also found that the electricity demand had extremely high correlation, which made standard models less effective. And when we tried to build multivariate models using variable with weather variables and all the three zones, the model become unstable. Finally, separating seasonal patterns from temperature as exogenous regression was challenging because they overlapped heavily.
One major lesson we learned is that high-frequency data behaves very differently from typical daily or monthly time series. The strong autocorrelation in 10-minute readings often dominated the models, making it harder for other signals to stand out. We also discovered that seasonality isn't just one repeating pattern. There are multiple layers happening at the same time. We found that temperature was correlated but sometimes too weak to meaningfully improve predictions. Classical models struggled when the data suddenly shifted levels, and finally we saw that forecasting multiple steps ahead quickly increases uncertainty.
Our analysis showed that reliable forecasting for this dataset is only achievable when the model directly captured the strong intraday seasonal structure. Daily ARIMA, SARIMA, and VARCAR approach struggled with the extreme autocorrelation and high frequency volatility. The Fourier plus exogenous regression model produced the most stable short-term result by learning 10 minutes cycle. Though it still smoothed sharp level shift. Overall, the project established a solid baseline forecaster and clarified the limit of classical time series method for dense operational load data.
Expanding the dataset to multiple years will help us capture long-term seasonal patterns that aren't visible in just one year. We also plan to include more exogenous regressors like holidays or regional demand to improve the accuracy of the models. And finally, exploring advanced methods such as LSTM, TFT, or hybrid models may help us handle certain shifts in the data more effectively.
Thank you everyone for watching the entire presentation. Let us know if you have any question in the discussion forum.